Hey guys, and welcome back to another video. Today we're looking at question 3148 on LeetCode. It's called maximum difference score in a grid. The question says you're given an m by n matrix grid consisting of only positive integers. You can move from a cell in the matrix to any other cell that is either to the bottom or to the right, so they're not necessarily adjacent. The score of a move from one cell to the next, so say C1 to C2, is calculated as C2 minus C1. You can start from any cell in the grid and you have to make at least one move. Return the maximum total score you can achieve. So they've given us an example grid here. It's a 4x4 matrix and the output for this particular instance is 9. And the way this is achieved is by starting from cell 0, 1. So we start from cell 0, 1. From 0, 1 we move to cell 2, 1 with the value 7, and so this move has a total score of 7 minus 5, which is set to 2, and then from the cell 2, 1 we move to the cell 2, 2, which is the adjacent square with the value 14. This move has a value of 14 minus 7, which is 7, and so the sum of the total moves, the sum of the score of the total moves is 9, which is our output. Now, the important things to note is that we have the constraint where we can only move to the right and downwards, and that we don't necessarily have to move to adjacent squares. So all of our paths, they can start from any square and end up in any other square, just as long as the final square is to the right or below the starting square. So I've just drawn some example pathways here. And our resulting output is the one pathway whose score is maximal. One other thing I just want to point out is that although we have this kind of relaxation where the squares do not necessarily need to be adjacent, observe that it doesn't make a difference whether the move is adjacent or not. Now what I mean by that is, take a move, let's say the move from cell 0, 1 down to 2, 1. So we've already clarified that that is a score of 2. But if I were to split that up into two separate legs, so from 0, 1 to 1, 1, and then from 1, 1 to 2, 1, we would have two intermediary scores. So the first leg would be 9 minus 5, which is a score of 4. And the second leg would be 7 minus 9, which is a score of minus 2. And again, the total score here is 2. Alrighty, let's look at the same problem instance they've given us in the example, see if we can gather some intuition about what our solution is going to be. So we have this 4x4 matrix, and we know that it's going to start at grid index 0, 1 and finish at grid index 2, 2, and the pathway, which I'm highlighting here, is the one that yields the optimal score of 9. Now I want to slightly change the definition of the problem we're trying to solve. This is all going to make sense in a second. Opt of ij, which is the maximum or the optimal possible score of some path that we guarantee ends at index ij of our grid G. So it's a more restrictive formulation. But the one thing you'll notice is if we calculated opt ij for every index pair, that is opt of 0, 0, starting from opt of 0, 0 all the way through to opt of 3, 3, then the maximum possible score is just the opt ij pair that yields the maximum value. And I've denoted the maximum score as S. That's the solution to the problem we're actually trying to find. If you think about this, this makes sense, right? Because if you calculate the maximum possible score of a path ending at every single possible index of our grid, then the maximum of these maximums is the score that we want. So let's try to hone in onto this formulation, opt I of j, for a second and see if we can devise some kind of a recurrence relation. Let's consider for a second, in our concrete example, opt 2 of 2. So the maximum possible score of a path ending at grid index 2, 2, which is the one with the cell value 14. And what can we say about such a path? Well, we know the path must have started somewhere above and or to the left of this grid index. And now let's consider which of the neighboring squares we could have been at prior to arriving at grid index 22. These are any of the cells to the left or above grid index 22. Our observation was that a unit move or a string of unit moves is equal to a single leap move. What I mean by that is moving from the grid index 20, say with the value 6, to 22, which is a score of 8, is the same as moving from the grid index 20 to 21, and then from 21 to 22, because that would impose a score of first 7 minus 6, which is 1, followed by 14 minus 7, which is 7, so a total score of 8. The same can be said for our vertical movements, and therefore we can restrict our definition by saying that the precursor move prior to arriving at grid index 22 must have come from the grid index immediately above or to the left of grid index 22. I've highlighted those two squares in pink. Where does this observation leave us with our opt22 definition? Well, opt22, again, is the maximum possible score of a path ending at the grid index 22 of our grid. And this path must have come from either to the left or above grid index 22. And again, at either one of these neighboring cells, we'd be able to identify a maximum possible score of some path ending at either one of these cells. In other words, opt2 of 2 could either be opt2 of 1 plus the score of jumping from grid index 21 to grid index 22, or alternatively, it could be opt1 of 2, that is the maximum possible score of a path ending at grid index 1, 2 of the grid, plus the additional score for leaping from the grid index 1, 2 to the grid index 2, 2. And in addition, the path that we're trying to find may not necessarily be an extension of an existing path ending at index 2, 1 or 1, 2, but rather the start of a brand new path where the index 2, 1 or 1, 2 is the very beginning, in which case the score of this brand new path is simply the score of the single leap. And therefore the final outcome for opt2 of 2 is, amongst all of these alternatives, the one alternative that yields the maximal score. And so we can wrap all 4 of these options inside of a maximization function. So now with this definition of opt2 2, we can take it and generalize it for the general case for opt_ij as follows. That is, we have opt_ij, which is the max of 4 options, the first being opt of I minus 1j plus the additional score from moving from the left neighbor to the current node, or opt_ij minus 1 plus the score of moving from the node immediately above to the current node, or the start of a brand new path from either the precursor node above or to the left of the current node. Alright, here we are in the LeetCode UI. Let's put together a solution. So we've identified a recursive dynamic programming approach where we said opt_i of j was equal to the maximum of a few things. So we said that opt_ij was related to a few possible subproblems. To do this, we'll first have to create our DP matrix, which I'll call opt, and the DP matrix will have 2 dimensions, m and n, which are given to us by the size of the input grid. Let's go ahead and initialize all the values in this table to 0. Let's initialize a maximum number and set it to a very small number to begin with. Now we can commence the bottom-up DP approach. One thing we didn't mention in our write-up was how to handle our base case for this scenario. We can define the base case as when we reach the very first cell of our matrix. That is, what is the maximal score of a path that ends with certainty at grid index 0, 0. If the path had to be extended from the left or the vertical neighbor of this grid, clearly there is no left or vertical neighbor, so the maximal score of such a path must be 0. And now we can commence the dependent step. So I'll go ahead and define 4 variables, which I'll call R1 through R4. And I've initialized them to very small numbers. And now what I'll do is populate the correct value for each of these variables. And once we've calculated our 4 options, we now need to take the maximum of all 4 options and set the value of opt ij as follows. So we've calculated the value that is maximal for opt ij, but our global maximum, which was this value max we had set initially to a very small number, we want to update with our new calculation for the current opt ij. That is, if this current calculated value for opt ij is the largest we've seen thus far, then we want to replace the value for max. And so that should be the value we can return once we exit our method. Let's go ahead and run. So we have a couple of errors. Okay, so I've just got to change this one here. Let's go ahead and run it again. Okay, index out of bounds error. So what happens here is when I is equal to, when I is greater than 0, and only then do we want to actually execute these I-1 terms, and same when j is greater than 0 is only when we want to access the j-1 indice. So what we can do is, what we'll do is we'll grab the I-1, we'll grab the matrices that are accessing the I-1th term, and we'll just put them in an if statement. If I is greater than 0, only then do we want to calculate these terms. Similarly, if j is greater than 0, only then do we want to calculate these terms, as that's the only time we can find a legal term for R2 and R4. So let's try that again, run. Awesome, we have test cases accepted. Go ahead and submit that. So we have a wrong answer. Ah, there we go. All right, R3. Lots of R3. Stupid mistake. So go ahead and run that again. Looks like it's passing all of those test cases. Amazing. Looks like the solution's been accepted. So that's the end of this video. Thanks to you guys for watching. I'll see you in the next one.